Do one quick check. One more advice, the camera should be in the top. You will see it. We are recording your screen, guys. So all your screen will show up in Zoom and YouTube. So this always should be to the top. Should do one more thing. It's not stable. It's slippery. Thank you so much, Naim. No worries, we didn't start yet. All right. There's a lot of chocolate today, so be ready to participate. Test. All right, good morning. This is another lecture in computer architecture course. Welcome, everyone. So today is a bit interesting topic, yet already you studied this maybe twice through your undergrad studies. It's about number systems. So when we talk about numbers in computer architecture, we always go to binary. Now let's see why throughout this lecture. This is just a quick reminder that we're going through 3 books, but the main one will be this very fundamental book. It's already considered in almost around the world. So in any university teaching computer architecture, they should go through this book. We're currently in chapter 1 for those who like to read the book before the lecture. So please jump into chapter 1, start reading over there. There are a lot of very nice exercises. And the next week, we'll take the first quiz, right? So we call it homework. So it's not really quiz. I will take it just in the first 10 minutes or so in the lecture, next one, right? So it will be basically on around every point we will take in this lecture, right? So hopefully last time, all of us agree that the definition of computer architecture is a bit loose. It's really not only hardware, but when we talk about computer architecture, it's really the algorithm that we run on the hardware, the transistor themselves, the logic behind it, even the data. The data itself is really important aspect in computer architecture. And we'll see why mainly in this lecture. So currently we'll focus, this is what we call, do you know the name of this? The whole thing over there? What do we call it? last time we mentioned it. And this is something mentioned already in our research group. This is really, we focus on the whole thing over there. We call it the compute stack. Compute stack, okay? So whenever we would like to do computation, we have to go through this stack or this tower, right? And make sure it's recording. I think you need to rotate the view. All right. So today we'll be focusing on data, and throughout the course, we'll go over multiple layer of this compute stack all the way to the what we call instruction set or ISA. These very important terms. What is this guy? Motherboard. Excellent. Oh, this is a nut bar. Be careful of nuts. All right. What do you know in this motherboard? What kind of component? What are the components that you know? Where are they? So on. Just name one. Processing unit. Where is it? Yeah. This guy? Excellent. Can you catch it? Oops, sorry. Excellent. So CPU, the most well-known guy. What else? Yes, please. PCI slots. These or those? Excellent. Yeah, these are the PCI Express. What else? Yes, please. Sorry? The DRAM slot, where are they? The right, the vertical ones, right? Excellent. What else? We need more people. Don't let me go back home with any of the chocolate. Yes, please. The IO slots. Excellent. All of these are IO, input, output slots, right? We use them for the, you like protein bar or nuts? Protein? Sorry. Yes, excellent. That's amazing. All right. So all of those are the main component of our computer, and they are very important for us for today. So the entire thing you see over here is just like house to accommodate all those components, right? This, the blue piece, we call it a PCB, so printed board circuit. Printed because we really print all those copper lanes within the board itself. So this can be plastic, can be something else, can be in green color, black color, blue, all of those different shapes. What is important, and normally we don't see, is the CPU itself. The CPU normally is hidden behind this guy. What is this guy? Heatsink, excellent. And what is in top of the heatsink? A fan. Why? To cool down the CPU or to dissipate the heat, right? And why? Why we need to do that? Sorry, say it loudly. Excellent. Less efficient. Not only less efficient, what else? Might make wrong calculation. Might make wrong calculation. Why? Noise, thermal expansion. We are going to the physics of the electronics, which is great, but there is something principle of DRAM operation, how the DRAM operate, how those transistors operate. And now, since we visit the term transistor, let's jump into the detail. But remember, always the CPU is underneath the heat sink. This is the heat sink. This is what dissipates the heat. And this is the fan just to pull out the hot air, okay? But the CPU is basically around those pins. Each of this is an input or output, each of those bins. Okay, so it's a pin, and on top of it, we put the chip itself or the CPU. And on top of the CPU, we put the heatsink. Top of the heatsink, we put that fan. Okay? And this is the CPU. It's basically just very thin layer of some stuff. Okay? It's very thin. It's not that whole block. What is inside it? If we dissect the CPU, what we'll find out. So this is the CPU. Those are the IOs. Sometimes it's underneath, and for most of the CPUs, it's really underneath. You will not see those legs. We call them legs because it's really a leg. Okay? You will not see them in the CPU. But most of the chip, you will see them. In CPU, we have many of them, so we cannot have them surrounding the CPU. We have to have all of them underneath that CPU. But once you dissect, this is a cover, just a lid. Just you can open it up, okay? And what you'll see inside is this way. And in reality, the CPU is only this portion, is only this little thing over there. That's the CPU. How about the others? What are these? What are these guys? Who's speaking? Yes. Depends. Those are connectors, just very thin copper wires, very thin. You can think about that as a guitar wires. So you can literally, you can really click on those wires and you can make sound out of it. But you will most probably cut most of them. Okay, they are very thin. Okay, and they are really the ones connecting the IOs from the CPU to the outside world. Okay. And this is when you get a closer look to the CPU or to this view, you will see something like that. So this is the CPU, and these are the wires we've been talking about. Now, when we look at the CPU itself from inside, what you will see? What you will see? It is a chip, right? It is a chip. What we will see inside the chip? Yes. Tiny lines of. Excellent. You're very close. What is it? Transistors. So this is the whole story of today. It's the transistor. Okay. This is what is really inside it. Okay. Sorry. Today I'm not good in basketball. All right. So what you will see over there is a multiple layers of metal, okay? A layer which is laid out horizontally, another layer laid out vertically, and so on. Sometimes 3 layers, sometimes more, and so on, okay? And we make out of those layers or connectors a transistor, and a transistor, you can think about it as really as a switch. Just on, off. That's it. That's the whole functionality of a transistor. Probably you'll study transistors in depth in some other courses, like digital system design or DSP or VLSI sometimes, and so on. They have many different names. But what you need to know about it is just as a switch. On, off, on, off. Now you can enable this on, off millions of times per second, okay? Now you can think about it as a source of electrical charge passing through some component, and through the gate, you are connecting or controlling that source flood to go on or off. As simple as that. Now, the beauty of today's computer that you really don't need to control transistor by transistor. Imagine you are doing that. And in fact, we were really doing that in the old days. We have a lot of vacuum tubes that you connect them as IOs, input and output, and someone needs to set and control every single tube as on or off. This way, how they insert an equation or a number that they need to multiply, okay? Today, we control all of these through digital data. I know this sounds like really trivial, but I really need to go to that very low level in order to motivate you why we really have binary system, for example. Why not something else? So transistors enable, there's a typo over there, enable on and off states in hardware. And that's why we need a low voltage and a high voltage. We need a ground and VDD. And a ground basically is a 0 for us, and a VDD is a 1 for us, right? Now, this is in hardware. In a software, we could represent exactly the same thing, but rather controlling the VDD and the ground, we just mimic it as 0 and 1. But we will have always the question of what is really 1? When we have as a 1, what is it? Okay, transistor is taking voltage, but what is 1? Anything that's not 0. Very simple definition. That's great. That's excellent. But what is it in value? We don't have any 0 and 1s in hardware. It's just a transistor, either a voltage passing or not passing. That's it. Then what is 1? Positive. Okay. Which is anything more than 1 or 0, sorry. Right? Yes, please. True value. Yes, but what is it? We don't have true. We don't have false. We have either ground or VDD. What is 1 here? VDD. What is the value of VDD? We can set it ourselves. They're very close, but we cannot set it. There is no way we set or control this value. Yes, please. Go ahead, Naim. 5 or 12. Very close. Very close. Maybe he deserved. Let's try protein bar. Building muscles. I don't want to knock any head. What is this guy? Raise your voice. Power supply. Excellent. What is doing? Supplying voltage to the whole world of computer, right? However, the voltage they supply is really not single value. So you can see really we have 5, we have 3.3, we have 12, and so on. So here we have 3 voltage. Sometimes we have more, sometimes we have less. Depends on what? Which hardware? The component. Why we need multiple of one? We already have the answer somewhere. Excellent. So now we have multiple components in the computer. None of them work exactly the same principle as other components. And all the time, we need to orchestrate all those components. We have a DRAM. Hey, DRAM, what is your operating condition? Oh, I operate on this frequency, on this voltage, on this power, and this delay, and so on, right? Hey, CPU, what is your operation condition? Totally different from what we have in DRAM. Totally different from SSD. Totally different from all of those worlds, right? And the power supply is responsible to obey all of those requirements. Hey, you operate on 5 volt? Take this 5 volt. And that 5 volt is the one that we represent all the time in binary. That 12 volt is the one we represent. That 3 volt, and so on. So it really depends on the component that we are targeting. So the value 1, it's really not a single value, but rather sometimes could be multiple values. And that is the beauty of simplifying the concept of analog into digital. We don't care what is the original value. Whatever it is at the end 1. So I care about 1. Now, when a programmer coming in, they just program in 0 and 1s. They don't care about all those analog values, right? What are those? Data. We have a lot of different types of data. Could be pictures, not fruits, but pictures, right? Movies, voice, could be even the things we explained in the last lecture, genomic data. Could be something else. Could be radioactive signals, some sensors somewhere, some camera, some edge devices, and so on, giving you a lot of data, right? It could be temperature, it could be noise, it could be radon, it could be anything like that. Now, the nice thing about when you implement all of those as a binary data or a digital data, now you no longer worry about anything related to the complexities of all those formats. This is something really important even today. You might think binary system is really something simple. Yeah, okay, they invented like 50, 70 years back. Why we should care? It's done. It's very old science. Why we are studying it in 2025? Only yesterday, we released this on our GitHub. Feel free to access it. This is a new way of encoding genomic data into something totally different. So in the old days, probably most of you or some of you know, especially those who are working on biology or genomic data, we had something called FASTQ. This is one of the standard, one of the norm that everyone is using in this field for about 25 years, okay? We find a new way how we could really convert this into something else that we call it fast and then R, so it becomes faster. Okay. It's really something very efficient, something that we reduce the size of all those genomic data. We talk about single individual 3.2 billion character, which is billion byte, which is like gigabyte, right? That's a single cell in our body. When you talk about the tree of life, then good luck storing this in any database. So this is really important topic, and purely we just format all the stuff we are talking about in binary. But we find a new way how we could encode those binary data in such a way we save it in a very little storage footprint. We could parse it, we could read it, we could write to it in a very quick way. So this is already public. Feel free to download it. The paper will be public soon, probably in 2 days or so. All right. Now when we talk about number systems, we have two types of numbers. One of them we call it positional numbers, and the other one non-positional. What are those positional? You just need to read. Yes, please. Binary and decimal. What else? Hexadecimal. What else? Octal, right? All of those we call them positional. Why we call them positional, we will see in a few slides. Okay? The other type is non-positional. What are those non-positional? Where we use simples. So there is no other way to implement them except just using different simples for different numbers. What are the examples of those? Any hand drawing. You could just like invent your own way. I wanted this one, this is 2, this is 3, this is 4, 5, 6, 7, right? Invent your way. As long as you represent each number with a drawing, that's a non-positional. What else? Roman numbers, right? And there are really many examples, especially from the old civilization. All right, now let's jump into the positional numbers. And when we talk about positional, the natural one is decimal all the time. Now, what is decimal number? Very trivial. Maybe I skipped a slide. Yes. It looks trivial, but sometimes it's very challenging, especially when you go to the binary and you want to go back to the decimal. When you go to hexadecimal, I want to go back to the decimal. Sometimes it confuses you, right? Let's see why. So this is a number, 4-digit number. We have 5, 9, 3, 4. Now, each of those, we call them a digit. And in decimal, the digit range is from 0 to 9. I know this is very trivial, but please pay attention, because now we're going to highlight the binary in the same way. And you'll see how you can invent your own number system, okay? Especially the positional ones. Now we call it decimal, which is to the base 10, okay? Now you could directly correlate the base 10 to the range of the digit. How many numbers we have in the range for each digit? From 0 to 9 means 10 numbers. So we have 10 numbers in the range, and the base is 10 also. So always, whenever the base, whatever number, 5, then the numbers in the range should be 5. Okay, that's one. The second thing, and this is why we call it positional, because in every position of those numbers, we have different meaning. And this is really important. This is what makes the huge difference between positional and non-positional. Over here, a 1 and 10 is really different. It could be totally different drawing, okay? But here, it could be the same. The 1 could be here, the 1 could be there, the 1 could be there. But the position of that one makes all the difference. So here we have ones, tens, hundreds, and thousands. And that has a big meaning, okay? What is the meaning with the ones, tens, hundreds, thousands, and go forever? So we always want to represent it as something really important, which we will see in the next few slides. However, it will make more sense if we convert that ones, tens, hundreds, thousand into this formula, which is the base itself to the power of something. And that something take another range from 0 to infinity. You could go forever. It's not limited as the range for each digit, okay? So we always start from 0, 1, 2, 3, 4, 5, go forever, okay? So let's see how we can represent this number in that formula. So it's very simple. We want to make sure first we are using the correct base, the correct range for each digit. And then we directly go to the first one from here, and we start with the base to the power of 0, because that is the first number in our range. 10 to the power 0 times 4. 10 to the power 1 times 3, plus 10 to the power 2 times 9, and so on. And this is really how we represent those numbers. Let's see it together. Yes. That is the equation, how we should represent it. That is a 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4, and so on. It depends how many digits we have here. We have 4. That's why we represent it using 4 terms. All right. Hopefully this is trivial for you. So let's see the binary. And I want really to show this stuff for decimal. So now we want to reflect it into the binary system. And then if I ask you to design your own number system, it should be really trivial. As long as you know what is the base, which is directly giving you the range for each digit. And this one is standard. This is common in all number systems. All of them should start from 0 to the power 0 to the power 1 to the power 3 to the power 4. What's changing is the base itself, right, which is this guy, and this range. So if just like came to my mind, let's design, I don't know, whatever number, a base of 5, a base of 7, a base of 8. Out of curiosity, I just want to design my own number, right? You should directly follow those rules. Let's see the binary one. So this is a binary number. Binary means 2 choices, right? So the base is what? Let's maybe use another color. What is the base in binary? 2. Excellent. So we have 2. I don't know if you can see. Can you see the 2 over here? Okay, perfect. Since it's 2, what is the range for each digit? 0 and 1. We always should start from 0, right? And then we count how many numbers based on the base. So 0 all the way to 1, right? That is what each digit can take, either 0 or 1. The base is 2. The range for the power is always 0 to infinity. Okay? I don't know why I write from right to left. It should be from left to right, but same idea. Okay? All right, let's convert this guy to the formula altogether. We always start from the right side over here because this is what we call, what do we call the digit to the right side, rightmost side? Sorry? Excellent. Least protein or not? Let's go with protein. I love protein. Okay. So this is what we call least significant bit, and this is most significant bit. Okay. So what we call it in short, LSB and MSB. Although this is bit, but we just use uppercase B. Okay. Don't mess with byte. Now let's convert this guy. What we will do, what is the base? The base 2. What is the power? We always start from 0. So 2 to the power 0 times the first digit, which is 1, plus. So let's write it all together. Here we have weird setup for the room. This should be going to the back, and the board should be higher level. Anyway, so we said the base to the power 0 times the first digit 1 plus, yes, base to the power 1 times 1 plus base to the power 2 times the digit, which is 0, plus, guess who's saying here? A lady voice. Please go up. Excellent. 2 to the power 3 times the digit, which is 1. Okay. I would like to encourage all of you to participate. This way, you really break down the fear from speaking up. Okay. This is very important. When you graduate, you have the ability to speak to audience with no shyness, no fearness, and so on. They always said in any talk, the first 2 minutes are the most important ones. Sometimes you forget what you have to say. Even for me. I've been teaching for, I don't know, 12 years, and I always have that fear. Doesn't matter, because you see, everyone is new to you the first day, right? That is the equation, how we convert the binary numbers into whatever numbers we would like to know. And this is the equation. You can follow up. If you are not convinced with this, you can follow up. Here, for simplicity, those numbers are the base to the power of something. And this is what we said. Least significant bit, most significant bit. Whenever you get confused where to start, which digit is this one? Is it the one to the right or the one to the left? Remember, LSB and MSB. If you are confused still, go back to the decimal number. So when you write like 1,235, which one has the least value? Of course, it's 5. This is 1,000, this is 5. So this is the least value. And that's why we have it as LSB. And this is where we should start with the base 0, because it's the minimum number, and so on. So we think that decimal is trivial, but it's always confuse the thing out of us. This is the general rule. Please follow it. I'm going to ask one question next week about it. So the digit, whatever that digit is, times the base to power something. The base is really correlated with the digit. So if the base is 2, we have 2 values. If the base is 9, we have 9 values. If the base is 5, we have 5 values, and so on. And always the value starts from 0 all the way to something based on that base. And the power also starts from 0, but has no limit. Does not depend on the base, for example. We have until infinity. It depends on the value itself, the number, the whole number, not the base, not the digit. So did you get why we call it positional number? Okay, this is very important, because the position of each digit is going to really differentiate the value and the base and the power. All right, now we want to go back and forth. Why? Because all the time, all numbers, all kind of data representing computer are in binary. But there is no way to give the user all the time binary data as output. So there's always should be a proxy where we have a binary in one side and the output should be something else. Could be imaged, could be text, could be voiced, could be video, it could be anything, right? And that proxy, who's responsible to build it? Programmers, right? But the programmers cannot see the binary, because the binary is hardware thing. It's stored in the DRAM, stored in the SSD, and so on. So we need someone in the middle to fix those things. And who should be? Who's that guy? The computer architect. The computer architect is building the whole computer in order to feed those binary data, to arrange them in a certain way in the DRAM and so on. So you can see the importance of all those topics to computer architecture, especially the data. All right, what is 6 in base 2? Maybe we can go faster now since we set the stage. So we are already going with this equation. Hopefully everyone now agree on this way, how we convert those numbers. What is 6 in binary? 6 is decimal. I want to convert into binary. Yes. 110. 110. Let's convert it together and see if this is correct or not. And then you get chocolate. Okay. All right. So we said first this number represented in binary. And normally when we say binary, we have to add that little superscript as 2. So it means this is binary system. Okay. Now, if this is binary, then the base is 2. The range is 0, 2, something, and something that should add up to 2 values. So 0 and then 1, 2, 3, 4. So then we already got the 2 value. That is the, what we call it, the digit. Okay. And the power is 0 all the way to infinity. Then we have a 2 to the power 0 times 0 plus 2 to the power 1 times 1 plus 2 to the power 2 times 1. And that gives you, this is 0 times 1 is 0, plus this is 1, plus 2 to the power 2 is 4, times 1 is 4. Oh, sorry, this is 2. So 2 to the power 1 is 2, not 1. And that's give you 6, and that's a correct answer. Yeah, you are too many. I cannot throw it. Please. Thank you. All right. So there is another way of doing it. It's basically to go to the highest value and then keep deducting from the number that we would like to convert. For example, what is the largest power of 2 that is less than or equal to 6? What is the largest number to the power of 2, or sorry, largest power of 2 that is equal or less than 6? So what are the numbers power 2? So we have 1, 2, 4, 8, 16, right? 32, 64, 128, 256, 1024, and goes on. Oh yeah, we forgot 512. Right? Excellent. So we pick a number that is less than or equal to, but should be the largest. So all of those are less than a 6. Which one is the largest? Is 4. So we pick 4. We deduct it from 6. The result is 2, and we move on. Now we have 2. What is the largest power of 2 that is less than or equal to? We have these two values. What is the largest? 2. So we pick 4. We pick the 2. Do we have any remaining value? No. So 2 minus 2 is 0. Done. So we only have these two values as in binary. Now we know that this is already the order of the binary value. So this is the first digit, second digit, third, fourth, fifth, sixth, seventh, eighth, and so on, right? So if we know those are the values, then directly 0, 1, 1. If we know that this is the value and this is not, then directly 1, 0, 0, 0. This is a very easy way. Even me, myself, I'm doing it until today. So whenever I came into a problem, this is a decimal, I want to convert it to binary, I remember those numbers, but I don't remember that equation. So I remember literally those numbers. So 1, 2, 4, 8, 16. I remember those. I put them down, and I keep writing the 1 and 0 based on those values. So this is a very handy way of doing it. This is one way of doing it. You can follow this example and see what's happening in there. But there is another way of doing it also. Let's see. If you want, we can go in depth into this. If you have any doubt. How many of you wants to go in depth into this? Very good. All right. So now let's take another example. This is 53 in base 10. Base 10 directly means the digit means from 0 to 9. The power means 0 to infinity. All right, so we have 53. Want to convert into binary? Yes? Question? Oh, you want to convert it? Okay, excellent. So want to convert 53. So the first way is the one we mentioned over here. 53. What is the largest number or power of 2? So 53, no, still this is less, less, less. Oh, okay. Now 53 is somewhere between this guy and this guy, right? Now what is the largest one? This one. This is still bigger. This is less or equal, and the largest one, so 32. Let's have a circle out around it. Now 53 times, or sorry, minus 32, 21. Now we are looking for power of 2, a largest number of power of 2 that's less than or equal 21. So okay, now it's somewhere between this and this. So 16, the largest, and less than or equal this guy. So let's have a circle. Now minus 16, 5. 5, no, no. Okay, this guy. This is the largest. Now this is minus 4. 1. We're looking for 1, and that's 1. 1 minus 1 is 0, done. So what are the number we choose? So 1, because of this guy, then 0, not chosen, chosen, not chosen, chosen, chosen. That is the number in binary. Extremely straightforward. There is no magic about it, right? Now let's see the second one. The second way of doing it, repeatedly divide by 2, and whatever left after you divide over 2 goes to the most significant bit. Okay, very easy. Let's see. 53 divided over 2. So 50, 25, right? And 3, 1.5. So that is 26.5, right? So what we will have? So we have 26.5, or whatever left, right? and then we'll have it into the most significant bit, the most significant bit. And we said the MSP is to the left side, so we have 1 now. 26 over 2, 13. Anything left? No. So we have 0. We have now 13. 13 over 2, 6 and something, right? So there is something left. So we have 6 and there's something left, then there's 1. Now we have the 6. 6 over 2, 3. Anything left? No. So we have 0. Now we have the 3. 3 over 2. It depends on the mindset. Some people find, oh, this is the easiest for me. Some say, no, they keep arguing that this is the easiest for me. So our goal is to give you all the ways, and it's up to you. There is no correct or wrong here. As long as all of you arrive to the same conclusion, done. So 3 over 2 is 1, and we have something left over. So we have 1. Then 1 over 2 is 0, and we have something left over, and that is 1. Did we make a mistake? Did we do wrong? Oh, the opposite.
Yeah.
Why it says the MSP? Oh, excellent. All right. So you could keep it the same way, but you flip the number. Or from beginning, you consider this is the LSP. And then the next one will go to MSP. So you keep going into the left direction. The left direction. Yeah, this makes sense, I think. We can keep the definition as is. So the next one will go to the MSP, which is to the left direction of the number. Okay, so let's do it again to make sure we get the number. Let's do it quickly. Yeah, but in the entire course, we fixed that. Don't go through this. We'll confuse them more. All right, so 53 over 2 is 26. We have 1 left. We can start from here. Okay, and now 26 over 2, 13. We don't have anything left. All the way go to the MSP direction. Okay, 13 over 2, 6. We have 1 left. 6 over 2 is 3, nothing left. 3 over 2 is 1, we have 1 left. 1 over 1 is a half, so we have 0 here, and there is 1 left. This way we got it correct. Okay, does it match? Yes. Now, which one is easier? 2. Perfect. Who says 1? Makes sense, right? So this is easy to divide over 2. There's no confusion about it. As long as you practice it well, then it's easy, straightforward. This one, you could remember this number, but I already make mistake here. So you could make mistake, you could make mistake. So whatever fed to your mindset, just go ahead for it, okay? All right. Any questions so far? Any question? Perfect. Can anyone read this number? This is not my personal number. Can anyone read it? Sorry. Excellent. When you want to tell to someone, want to just say it out to someone that this is my phone number. You say it this way: 1, 3, 4, 5, 6, 7, 8, 7. How you say normally the numbers in the US? Right? 3 digits, and then 4, right? So this makes more sense. You could also represent it this way, but to still say 3 digits, 3 digits, 4 digits, right? Now, why we do it this way? Is it just because US different from anywhere in the world? They use inch, they use mile, they use all of these stuff. Yeah, they do have this country code, right? Sometime here they have 9 digits, 15 digits, 11 digits. It depends on the population, how unique you could get those numbers. Some countries, they have like 1 million population. They don't need to go that far, right? But actually, the way the US state that number really makes sense. It's not just because they are different, right? And why is that? Let's see a more complex example. And tell this number to your friend. There's no way just saying 0, 0, 1, 1, 0, 1, 0, 1, and so on, right? What is a better way to represent it? 4 bits, right? 8 bits, 16. Make it a little bit easier. What could be done better? What else we could do to make it better? Remember the drawing, right? So the ancient guys were really smart. It's not just like trivial drawing and that's it. There's an idea behind it. So every time you have something bulky, something really huge, something big, you could just replace it by a single item and done. Why should care? Why should write a whole sentence like, I'm hungry, I want to have breakfast? Just to draw sun or something. That represents that whole sentence and done, right? So they were really smart when having that compact representation. And we will do the exact same thing over here. Instead of representing this whole chunk of binary data, 1, 0, 0, 0, 1, 1, 1, 1, and so on. This is something huge. You cannot represent it. We'll just go with something called hexadecimal. And that's the whole idea behind hexadecimal. So if someone asks you, probably they don't teach you this, like why we have hexadecimal. Some people say, oh, yeah, it's just a different number system. That's it. No, in fact, the way we invent it is basically we want to represent the binary data in a better compact representation. How we represent hexadecimal. Again, let's go back to our story directly. What does mean hexadecimal? 16. So what is the base? 16. Excellent. Let's use now a different color. I forgot the green, maybe in my office. Okay. Yeah, let's use this. So the base is 16, right? Now, what is the range for each digit? Directly 16, so we start from 0. You don't have to think about it even. 0 all the way to until we got 16 value, which is 15. Normally the value minus 1 because we start from 0. Okay. What is the power? Still the same, 0 to infinity. Okay. Now, think about this range, 0 to 15. And that's the range for one digit. So 0, 1, 2, 3, all the way to 9. Makes sense. Yeah, single digit, can we have 9? How about 10? How we can have it in single digit? A. Excellent. Now we need to find a solution with this guy. Maybe we can erase this. Maybe we can use this. So with the 10, because we cannot represent in a single digit, right? So we have to convert into A. Likewise with 11, B, C is 12, D 13, E 14, and then the 15, the last one is F number, right? So you have to remember why we are doing it. If you think about it deeply, you will understand that hexadecimal makes sense. And why I'm explaining all of that, if I ask you to design your own number systems, you should be careful about that. Remember, this is the range for a single digit. And if it doesn't fit, if it has like 3 numbers, 2 numbers, 4 numbers, you cannot fit them in single digit. And then you find You have to find a really smart way how you represent those 2 digits into 1 digit, which is what we are trying to do over here. Right? So another way to think about binary system and hexadecimal is to divide the number into 4 bits, and every 4 bits convert it into decimal, and then pick one of those numbers. That's one way to think about binary and hexadecimal. So divide the number into 4 bits. Each 4 bits represent them into decimal, and from decimal, pick one number from that range, whether it's 0, 10, 11, 15, whatever you want. That's one way of converting binary into hexadecimal. Let's convert this guy. First, divide it into 4 bits chunk. 4 bits, 4 bits, 4 bits. Okay? And doesn't matter if you start from right or left. But it makes more sense to start from right because sometimes you have left over that might not fit 4 bits exactly over here. So if we start from LSB, we have 1100. What is it in decimal? Remember, if you ever forget, remember this sequence, the one in red, and try to match that with over here. So we have 1100, so it means 1, 2, 4, 8. This is 1, 1, and this is 0, 0. It means 1 and 2, so 3, right? So we have 3. Now 3 into decimal, out of the range from hexadecimal, stays the same, right? 3. All right, let's continue. 0, 1, 0, 1. What is it in decimal? 0, 1, 0, 1. So we have 1 and 1. 2 and 8, it's 10. 10 in decimal, in hexadecimal. Remember that range at the top? So it's 8. Why we do it this way? Because 2 bits, 2 digits cannot fit into 1 digit. So we have to find alternative ways of doing it. 0, 1, 1, 0. 0, 1, 1, 0. 0, 1, 1, 0. 2 and 4 is 6. And 6 into hexadecimal stays the same 6. That is the number into hexadecimal. Okay? Right? Do you have any question? So it's extremely easy. Divide the number into 4 bits. You can start from LSB, MSB, doesn't matter as long as you guarantee it's divisible by 4. Okay? So it's better to start from LSB to avoid any confusion. And then convert into decimal. From decimal, just pick one numbers out of that range. As easy as that. This is extremely important for your processor. And that will be your first assignment to support this operation. We really want to convert binary into decimal, decimal into hexadecimal, binary into hexadecimal, and all these operations. That one side of your processor to do that. The user might just insert 10 in base 10, right? Or 15 in base 10, 15 in base 16. You cannot handle any of that in the DRAM, CPU, and all this stuff. Everything should be in binary. So you should support always conversion back and forth, okay? Remember that. And this will be really your first assignment for the processor. So if you have any questions, just say it out loudly. That's the hexadecimal range. Please, as a computer architect, you always need to reason why we are doing this. And please remember why we are doing this hexadecimal differently from 0 to 16, okay? Or 0 to 15, sorry. That's the range for all those numbers. I don't know anyone in my network who remember those numbers. I hope you don't remember them as well. So just go the easiest way and try to convert them using this method. If you want to remember this table, good luck. It's easy to remember, easy to enumerate, because like you can see, like we are really enumerating the position of the 1, so 0 or 1, and then 1 to the next digit, and then enumerate more or add 1 basically into that number. This is how you get the whole list. And normally, like we can go from the first digit, it's either 0 or 1, and then either 0. And now we are done with this. So we go to the next digit. It's either 0 or 1. And you need to enumerate this digit and move on from there. So it's easy to do that table, but why we need to do that. Just do this conversion to be way easier to convert any number into that. All right, let's take quick practice how we convert this number. Remember, this is the base 16. We normally write it this way, 16. However, there's an exception into that. We will go into it soon. So when I convert this is hexadecimal into binary. So what we should do? So we know how to convert from binary to hexadecimal. Now the opposite. FA4. What should we do? You got chocolate, right? Let's find someone else. You hide it? Yes, please. Go ahead. What is the base? Excellent. Excellent. So you see, whenever you are confused or you are not sure of the way you want to use, directly go to our story. That's why I like to emphasize it a lot in the beginning of the lecture. Okay, this will solve any number system. Doesn't matter if you study it, if you don't ever take it, or so on. Very simple story. What is the base? What is the power? What is the digit? Done. Okay. Now let's do it. So what is the base? Base is 16, right? It's already given. You don't have to think. The digit, if it is 16 directly, we have from 0 all the way to 15. That's the allowed range. And remember our story about the things doesn't fit one digit. What else we need? We need the power, right? The power always from 0 all the way to infinity. All right, now let's start with the LSB, because we need to start from power 0. That's why we start from LSB. So we have a 16 to the power 0 times the digit. What is it? What is the digit we have? 15. Excellent. Who said 15? Okay. You didn't get hot chocolate today, right? I have one for you, one for you. So we have 2 left. All right. So 16 to the power 1 times, what is the next digit? A. A is what? 10 plus 4, right? So 16 to the power 2 times 4 equals something. That something will be in what? Which number system? Decimal. Excellent. So we'll have the decimal now using that formula. And then the decimal is very easy to convert into any one of those. Could convert into binary really quick, right? So that is the second method, right? So excellent, you mentioned it. You can always think about this way as a reference for you. Whenever you are confused, just go back to this formula, convert the number into decimal, and decimal to anything. It's really easy, straightforward to do it. Okay. However, you could go the easiest way. You could convert each of those digits into 4 bits into binary. Remember, 4 bits in binary represent those hexadecimal numbers. And that's the whole story why we have hexadecimal, just to shrink down, to compact all those ones and zeros. Okay? Protein or nut bar? Excellent choice. Oh, great. I practice my skills now. All right. Yeah, I don't want to go through this, but this is something you'll experience soon. Once you start programming for your assignment, you will know that we don't have superscript in programming. So you cannot have just the base 16, as we were mentioning somewhere. You cannot just say like number, this number, for example, you cannot just say 10 or to the base 16 or to the base 2. not just say 16 over here, right? Okay. But we do it in programming. We have to do this kind of what we call prefix. Let me highlight. So for hexadecimal, we use 0x. Whenever you see 0x before any number, it means this is in hexadecimal, which corresponds to this guy. So this way or this way, both of them are acceptable. But in programming language, we cannot write it this way. We have to write it this way. In binary, 0b. In decimal, what is it? What is it in decimal? I don't have chocolate, sorry, but what is it in decimal? X. No prefix. Natural, right? No prefix. So no prefix could be directly decimal. But might be some other ways to represent decimal, which I don't know now. You can ask ChatGPT and see. But normally, if you write it without any prefix, that is directly decimal. This is the default. How about octal? What is octal? Normally 0, O. 0, O. Okay? O for octal. Makes sense. But this is different from programming language to another language. So some languages, they have their own syntax. So be careful with that. Yes, please. Let's see. We will issue the assignment, the exact PDF, and we will go over it. Okay? We'll ask you exactly what you need to do. But will be very soon. All right. There's some terms like, it's up to you if you want to know it, like we call this a byte, and I'm sure all of you know that. This is what we call nibble, which is 4 bits out of 8. And then single one of them, we call it bit. And then there is LSB and MSB. And what is more important than this is this, it's up to you. You can know it. You don't have to remember it, but it will make everyone's life way easier if you know these things. So you start from the power 10, it means kilo, 20 mega, 30 giga, 40 terabyte, and all these stuff. Okay, so it's easy to represent the number using this way. Now you can convert any number into this formula, even if it doesn't add up to 10. For example, 2 to the power 12. What is it? If you are very good in math, you would say, let's have it into 2 to the power 10 times something, right? Times something. Because this, we already know it, it's kilo. This is the first power, so it's kilo directly, right? Times 2 to the power of 2, right? This is in math already the same thing because the base is the same, so you can add up the powers, right? So 2 to power 10 plus 2. So this way you can say it's 4 kilo something, byte or bit or whatever you would like to say. So you can convert any number into these formulas. This you don't have to remember. We'll not ask you about all of these, but this will make you sound like more professional when you use them. There is one important thing in your processor. Again, it's not a magic. We are going to issue the assignment PDF, and you will see all those instructions, what you need to implement. But it's better to make you ready before you have the assignment. There's something called multiplying by base. If you have a binary number, and I ask you to multiply that number by 2 in decimal, what you would do? A trivial way to do it is really to convert the number, the binary number, into decimal, because our logic, always, our brain used to work on decimal, so it's easy for us to go back to decimal. So you convert the binary into decimal, and then multiply that number by 2 in decimal, get the result, convert it back into binary, right? It's way easier. Like, can you multiply this by 2? This is binary. So it makes sense. Let's say 1, 2, 4, 8, 16, 32, and so on. Let's convert this. This is 0, 0, 1, 1. So 4 and 8 is 12. So that number is 12. Now it's way easier to multiply it by 2. 12 times 2 is 24, right? Now convert this into binary. 1, 2, 4, 8, 16, 32. So 42 or 24, sorry, is located over here. So that is 16. So we'll choose 16 first. 24 minus 16 is what? 8. So we have it this guy. So we have like 1, 1, 0, 0, 0, right? That's the result. Am I going fast? Should I repeat it? Way easy, trivial, right? What did you notice between this and this? Who's saying? Excellent. You just add 0 to the right side. 0 to the right side. What does it mean? When you add 0, it looks like you are shifting the number to the left. You are shifting the number to the left. Okay? So multiplying by 2 in binary is really shifting the number to the left. As easy as that. You don't have to do decimal. You don't have to convert back to binary. You don't have to do all of that. Just shift the number to the left. That is multiplying by 2. How about dividing by 2? Shift to the right. As simple as that. Shift the number to the right. Just lose whatever that bit is, and done. That is dividing by 2. You want to try it? Or you take it home? Maybe you take it home. Let's go over this last slide, and then we'll be done with the lecture. This is something I like to play myself. I'm really curious about binary and all those numbers. I do it a lot in genomic field, because this is something will make your data very efficient. So just pick that logo, just that picture. Try to use this command in shell if you have terminal, or Linux. I don't know in Windows if it works, but if you have Mac or Linux, should work directly. So hex dump minus C uppercase, and then the file name, whatever this PNG logo. This is from the website. You can get it directly. And this is what you will get. This is really what is happening in that file. So this picture, this is what really the computer can see, which are the things in the middle. This is just an index, just like line number. It's not related to the file. This is line number. And only those are the things that are the hexadecimal that belongs to this picture. This is just a representation in ASCII, so it's convert each of those into ASCII character. So this auxiliary, this is auxiliary, and this is the core thing that we are looking for, only those things. Of course, the file go very long, so this is just ahead of the first few lines. Now, something very interesting you can do with those, you compress the data. You don't have to keep that data as is. How you compress binary data? The easiest compression ever is run length encoding. Run length encoding. What does it mean? It means just count how many repetitive numbers you have. So zeros, how many times we repeated? 1, 2, 3, 4, 5, 6, 7, 8. Replace all of that with 0, 8, or 8, 0. What does it mean? It means I have 8 zeros next to each other. Ones, 1, 2, 3, 4, 5. So 5 ones. And you go on like that. This way, you could represent this whole string using just a few digits. That's one way to do the compression. I will leave you with this paper. If you are really interested in research, you can read this paper. You can see that even up till this year, we see papers on compression for computer architecture. This paper is from MIT. It's a really important one. You can read it if you are interested in this. This is another paper with a YouTube video about it, so you can read it. Both of them on data compression and how you convert those binary to decimal and all this stuff. So this is not old science. There are a lot of hot topics you can do with just binary to decimal, decimal to hexadecimal, and so on. Remember to check out our new work. And when we release the paper in 2 days or so, I'll send you the link to the paper. Yes, please. Monday. Monday is not off, right? Yeah, so Monday we'll have the quiz in the first 10 minutes. It will be very simple around all these points. Hopefully I cover everything needed. As I told you, I'm not here to challenge you, so everything will be from the topic of today. There's nothing from outside the book. Yes, please.
You have like snow and ice forecast weekend.
Oh yeah, guys, this is a very important point. Thank you so much for reminding me. There might be severe weather this Friday, Saturday, Sunday, coming to Georgia, Texas, and all these states. Okay, this is really serious. They said snow will be like 1 to 2 centimeters thick. And you know, Georgia is not ready for those kind of conditions. So last year, we take that day off. So in case it happened to be on Monday, which is very unlikely, they said only Friday, Saturday, Sunday, we might convert into online or cancel the class. Okay, I'll let you know over iCollege, so please pay attention to that. Okay, it will be university-wide thing. It's not only our class. Thank you so much, everyone.
Why do we build?
Excellent point. Yeah, I wish I can explain it to everyone. So in the old days, the processor couldn't fit really 32 bits or 64 bits, which is multiple of 4. So in the old days, we could fit multiple of 3 bits. That's why we have the octal system implemented, not the hexadecimal. So the octal, we represent, instead of every 4 bits, we use that range. In octal, we use every 3 bits, that range. So whenever the chunk of data divisible by 3, we could use octal. If it's divisible by 4, we could use hexadecimal. That's an excellent point. Maybe I can emphasize it next lecture as well.
Forgetting what it's called. But basically, when you have the supercomputer, instead of 2, you will 3.
So it really depends on what you represent in the DRAM. In DRAM, normally, we don't represent 4 bits or 8 or 16. We represent like 32, 64, sometimes 512 kilo as one lane, like one axis, one clock cycle. We fetch 512 bits, right? So it really depends on that. If it is divisible by 4, excellent. You can represent everything in hexadecimal. If it is not, you'll have a problem. Either you add some zeros at the end to make it divisible by 4, or you can use octal system, so it's divisible by 3, for example. If it's not this, not that, you need to pad with 0 to make it divisible by 4, and then you can use hexadecimal. There is always a purpose why we use this number system over others. Okay? I'm trying to avoid attendance the first 2 weeks because I receive a lot of emails that we're still not sure if we will come. We are waiting for visa and all this stuff, so I don't want to miss for some students. But probably next week we'll have the attendance, which is the quiz, the homework.
Oh, okay.
All right. We start from there because I think this week is the last day to drop and add the course. Yeah. This lecture. Yeah. Yeah, I'm sure all of you already studied this maybe 3 times, 4 times in undergrad, but I want to make sure that you have the same way converting so we speak the same language, basically. Right? Thanks a lot, guys. Stay safe. Thank you so much, Naeem.